you'll write down for each species you'll do a material balance. And we're going to go through a couple of examples today, if you don't remember what this looks like. Except now we need to add an additional equation, which is what? The energy balance. So are there multiple energy balances or just the one? Just one. Not an energy balance for each species. So the energy balance when there's multiple reactions looks like this. So this would be for a tubular reactor, PFR or PBR, which is why we have the change in temperature with changing volume. We still have this same term, which represents what? And before, what we had for a single reaction, what we had was the rate of consumption of A times what? Minus the delta H of reaction at that specified temperature. And what did we call this term?
Constant independent temperature?
No, I don't mean this. I mean the
Heat generation.
product.
Heat generation.
Yeah. This is our heat generated. And so the sum of those represents the driving force to affect the temperature. What is the resistance? The heat capacity terms, right. And what we had was the sum of the flow rates for each species in the system. And of course, we would often rewrite this such that the flow of any individual species was equal to the initial flow rate of A, the ratio of the two inlet flow rates, and then one plus the stoichiometric factors times the conversion. No, wait, this is wrong. Sorry. I had the parentheses in the wrong spot. I guess I'm using J, right? Yeah. And so anyways, that was how we would ultimately have what you guys have been using the last few weeks is down here it would say typically theta times the heat capacity. And there would be an initial flow rate of A term out in front, which may or may not cancel depending on the rest of the reaction. So again, this is valid for a single reaction. What do we have to change now to incorporate multiple reactions taking place simultaneously? Does Q change? No, right? That's purely a property of the heat transfer in or out of the system. It doesn't know anything about how many reactions are taking place, or even if there are reactions taking place, right? If we didn't have any reactions, this would just be a heat exchanger. Does the resistance change in the way that I wrote it? No, because I already wrote it as we would write it for multiple reactions, which is that we wouldn't want to do this. This is what you would do for a single reaction. You don't want to do that for multiple reactions because conversion is an ill-defined parameter when you're dealing with multiple reactions. So there's no reason to rewrite everything in terms of conversion. And we didn't do that when we were dealing with multiple reactions in an isothermal system as well. What about the heat generation term? Right. So now, what do I need to put here instead in order to accommodate multiple reactions? It's a summation term. What am I summing over? Species or reactions? Reactions. Pretty sure the book says Q, so Q is number of reactions. And then what goes inside there? The rate of each reaction, written in terms of some species. So we're going to talk more about that. But now that I'm dealing with multiple reactions, it's not always obvious like A or B or something. Often in the book examples and stuff, it's going to be A. But you have to write the rate in terms of a species. And then what do I multiply that by? Negative delta H of that reaction at the temperature of the system. And then again, this is specific to a reaction, and I have to write it in terms of a species. And we'll get into what does that mean, writing a delta H reaction in terms of a species. It's not complicated. So any questions about this? So it's not a very big departure from what you've been dealing with. Now the only difference is that there's going to be multiple reactions, and so each one of them can generate heat or consume heat. Obviously this is written as generated, that's why you have that minus sign in front of delta H reaction. But they can also consume heat if they're endothermic reactions. So what do we mean by this is that what you're writing here this is the moles of J generated or consumed in reaction I divided by volume and time. Right, so that's a rate. It's moles of something made or consumed per volume per time. And so I have to multiply that by the energy released or consumed reaction I per moles of J generated in reaction I. And so what cancels, right? This cancels with this, and what you're left with is energy released in that reaction per volume time. So again, when we get to the examples, you'll see a little bit more of what we mean by that. But you just need to be clear on what is the basis for that delta H of reaction. So we had similar confusion with what is the basis of a rate constant, right? All right, so that's for a tubular reactor. For a CSTR, it's similar, but a little bit simpler. So now we don't have a differential for temperature, so we can simply set it to Q to 0, which is because there's no accumulation of energy within the system. So you still have Q. You have this term representing the amount of heat that's coming into the system. So this is all about the inlet, and this is all about what's generated within the system. So any questions about the equations that are important here? And then we're going to work through an example for a CSTR in which you don't need to solve differential equations. And then we'll work through an example with a PFR in which I'll pull up Excel and show you how you set this up. It's a little bit more complicated, but the same idea is what we've done, is what we've been doing. Yes?
For the CSTR, we're putting it in terms of FA not theta still?
Yeah, that's fine. You can, theta doesn't depend on conversion. Conversion is the thing that you need to avoid. But you don't have to do that. You could have put here instead simply the sum of the heat capacities times the initial flow rates of each species times T minus T naught. But often it's nice to still define the inlet in terms of the flow rate of a single species and then a bunch of thetas. Again, the things that you want to avoid is really conversion and other things that can kind of have a foggy meaning, such as epsilon or delta. You don't really see those in problems for multiple reactions either. You do the stoichiometry section differently, and again, you'll see that in these examples. So any other questions? Okay, so let's do an example for a CSTR. And this will be a little bit of review of just how do we handle multiple reactions for isothermal reactions too. All right, so the example we're going to deal with is a series reaction. We have A goes to B, goes to C, and it's elementary, it's liquid, it's occurring in our CSTR that has some sort of heating.